Welcome to this explainer. Today, we're taking a completely different approach. We are blending ancient warrior wisdom with modern exam strategy to help you slice through Cambridge computer science past paper questions with absolute undeniable precision. Whether you're sitting for syllabus 0417, 0478, 2210, or 9618, the core strategy to dominating the paper remains exactly the same. But look, before we get into the code, we need to talk about why so many smart students lose easy marks. Let me introduce you to two archetypes I see all the time. First, we've got Alex. Alex has a brilliant memory, but Alex uses the overload approach, delivering raw computer science facts without any real analysis. It's just a massive brain dump of everything they know about algorithms onto the page. The examiner gets exhausted just looking at it. Then we have Sam. Sam knows the material cold, but Sam rushes. Sam completely misses the command word requirements in the question, answering what when the question clearly asked why. Sound familiar? Today, we are going to deconstruct these flawed approaches, get inside the examiner's head, and show you how to become a true algorithm architect.
Here's our strategic roadmap for today. We're going to hit the program lifecycle, move into decomposition and design, break down standard algorithm methods, clarify validation and verification, and finally, conquer testing and trace tables.
All right, Section 1, the program lifecycle. This is where we move from the high-level conceptual inception all the way down toward the actual code.
Okay, let's dive into the 5 distinct stages of the program development lifecycle. Every digital architect, every coding samurai has to follow these. Stage 1 is analysis. This is where we investigate the current system and specify what the new program actually needs to do. Stage 2 is design, using abstraction to build structure charts and pseudocode. You're not coding yet, you're blueprinting. Stage 3 is coding, actually writing the iterative suite of programs in your chosen high-level language. Stage 4 is testing, stress testing the logic to ensure it works under absolutely all conditions. And finally, Stage 5 is maintenance, keeping the system relevant and bug-free over time. Now, when answering exam questions on these stages, top-tier students don't just list facts like our friend Alex. They use a specific framework called PEAL. That stands for Point, Evidence, Explanation, Link. You make your point, you provide evidence from the specific scenario in the question, you explain how the computing concept works, and crucially, you link it back to the command words requirement. Before we continue and see this in action, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Let's look at exactly how precision in terminology earns top marks. Check out the bottom answer here. This is a classic SAM mistake. Imagine the exam question asks you to describe the purpose of analysis. The flawed answer says, a systems analyst will use interviews and questionnaires to find out what is needed. Okay, it's full of facts, right? But it completely misses the command word purpose. An examiner is going to give that a maximum of 1 mark, maybe 0, because it describes how analysis is carried out, not why it's carried out. Now look at the high-level answer on top. This uses the PEAL framework beautifully. Point. Analysis is used to investigate the problem. Explanation, and find out what the program needs to do. It's crisp, it's targeted, and it directly slices through the question's requirement like a katana. It gives the examiner exactly what they asked for.
Moving on to Section 2, decomposition and design. This is all about breaking down massive complexity into manageable pieces. Decomposition acts as the absolute bedrock of top-down design. It's the process of dividing tasks until each subsystem performs just a single, isolated action. Think of any complex problem you've ever faced. To beat it, it must be decomposed into inputs, processes, outputs, and storage. Let's go back to our friend Alex. Imagine Alex was asked to define decomposition and wrote, "It's making things smaller so you can code them faster." That is a 0-mark answer. It's way too vague. How would we rewrite this live using our PEAL framework? It should sound more like this.
Point.
Decomposition is the process of breaking down a complex system into smaller subsystems. Explanation. It divides the overall system down to the level of basic inputs, processes, outputs, and storage. Link. This allows the complex problem to be more easily represented, understood, and ultimately coded as single actions by a development team. Boom. Full marks, every single time.
Once you've decomposed the problem, you have to use formal methods to design the solution. Flowcharts are the visual representation of your algorithm's logic. You absolutely must memorize these standard symbols for your exams. There's no way around it. We've got the oval terminator for start and stop, the rectangle for a process like mathematically assigning values to variables, the slanted parallelogram for input and output, and the diamond for a decision. Now listen closely, because this is where people mess up. The decision diamond is critical. It always has two flow lines coming out of it, usually a yes and a no, forming the basis for selection and iteration loops. And here's a pro tip. If your flow lines don't have directional arrows on them, the examiner will penalize you. They can't assume which way the data is flowing. Precision is your weapon here. Don't throw away marks on sloppy drawing.
All right, moving from flowcharts to pseudocode. Here, we build our design using simple English keywords and mathematical operators to represent complex logic. Let's get one thing straight. Pseudocode is not Python, it is not Java or C++. It is a standardized, language-agnostic way to express logic. You need to be completely fluent in assignment using that left-pointing arrow. You need to master conditionals like if, then, else, and case of. And you absolutely must know your three types of iteration. For to next is for a known fixed number of loops. Repeat until is for an unknown number of loops where the action must happen at least once because the condition is checked at the end. And while do end while is for an unknown number of loops where the action might actually never happen if the condition evaluates to false right at the start. Mastering these is your blueprint for success. Stop scrolling, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Let's jump into Section 3, Standard Algorithm Methods. This is basically opening up the developer's toolkit.
These are your fundamental tools, the standard algorithm methods that form the building blocks for practically any processing task you'll face in the exam. You need to know these by heart. Totaling adds values to a running total, and hey, always remember to initialize your total variable to 0 outside the loop, or your logic is broken from the start. Counting increments a counter, usually by 1. Finding maximum and minimum is a classic question. The trick here? You have to set your initial maximum variable to an impossibly low number, and your initial minimum variable to an impossibly high number before the loop starts. Then we have the heavy lifters. Linear search, which inspects items sequentially one by one, and bubble sort, which compares adjacent items and swaps them if they are in the wrong order, bubbling the largest values to the top.
Time for an interactive workshop. Let's look closely at this linear search pseudocode. We're going to do a data scan challenge. Imagine a 60-second countdown timer on your screen right now. I want you to scan this complex pseudocode and extract the core trend. What is the single condition that makes this loop stop? Go ahead, pause if you need to. All right, time's up. When you scan through the repeat until structure, you have to cut through the noise and look at the variables controlling the exit condition at the bottom. Did you spot the line? Until found equals true or counter greater than class size. The core trend here is a dual exit condition. The loop terminates either because the Boolean flag found becomes true when a match is successfully found, or because the counter exceeds the total number of students, meaning we've checked every single item in the array without success. Slicing through the code to find these control structures is a vital, high-level skill.
Section 4, Validation and Verification. This is all about ensuring data integrity.
Okay, contrasting validation rules against verification checks is absolutely critical because it keeps your data pure and it's a major point of confusion for students. Time for challenge number 2, find the flaw. I'm going to read you a sample paragraph written by a student and I want you to find the sentence that's losing the marks. Ready? To ensure the password entered is correct, the system uses validation. It performs a double-entry check where the user types the password twice. It also performs a length check to make sure it is at least 8 characters long. Did you catch the flaw? The flaw is in the first 2 sentences. Double entry is not validation, it is verification. Validation ensures data is reasonable, like the length check, making sure it fits the database rules. Verification ensures data hasn't changed during the entry process, like typing a password twice to ensure it matches your intended keystrokes. So to summarize concisely, a range check is validation because it automatically ensures numerical input falls between a specified upper and lower limit. A screen check is verification because it is a manual visual comparison by the user against the original paper document to ensure accuracy. Validation checks logic, verification checks consistency. Know the difference.
Section 5, Testing and Trace Tables. This is the climax of our journey, stress testing our algorithms.
You must run these 4 specific types of test data through your system to comprehensively vet your code's logic. If your system accepts exam percentages from 0 to 100, you need precision testing. Normal data would be something standard like 50. Abnormal or erroneous data would be text like hello or an out-of-range number like 150. Boundary data is the absolute trickiest. It catches everyone out. It tests the exact edges of the logic. For a greater than 50 rule, your boundary values are exactly 50, which should be rejected, and 51, which should be accepted. Extreme values are the largest and smallest accepted values, so exactly 0 and exactly 100. Understanding these definitions is rule number 1. Now for challenge number 3, speed writing. Imagine a 30-second timer on the screen. Your task is to write one perfect Peel paragraph explaining boundary data for a system accepting inputs from 1 to 10. How would you do it? You'd say, point, boundary data tests the limits of the acceptable range. Evidence. For a 1 to 10 system, boundary values are 0, 1, 10, and 11. Explanation. It tests the data just inside and just outside the acceptable boundaries. Link. This proves the system's relational operators, like greater than or equal to, are functioning perfectly.
Let's act as a human computer for a moment. We're going to walk through a dry run using a trace table to record the result of each variable step by step. A trace table forces you to slow down. Each column represents a specific variable. Every time a variable changes value in the loop, you write the new value on a new line in the table. Never ever erase the old value. The entire history of the variable's state needs to be visible to the examiner. In this trace table, let's say we are feeding the array data 7, 11, -3, and 9. Notice how the small variable updates. It starts at an extreme high of 10,000. Then it compares the first input, 7. 7 is smaller than 10,000, so small becomes 7 on a new line. Next loop, the input is 11. 11 is not smaller than 7, so small stays 7. We don't write 7 again, we just leave the cell blank or move to the next variable that actually does change. Finally, it hits -3. Small updates to -3. The output column only gets written in at the very end when the print statement is finally executed outside the loop. Slicing through a trace table line by line like this is the ultimate proof of your algorithm architecture. It shows you completely understand the state of the machine.
All right, we've covered a massive amount of ground today. Let's recap the complete computer science answering system. There are 3 rules that guarantee top marks. Rule 1, command word decoding. Don't be like Sam, answer exactly what the verb asks for. Rule 2, Peel framework application. Structure your paragraphs with point, evidence, explanation, link. Rule 3, time management matrix. Don't be like Alex. Don't waste 10 minutes brain dumping for a 2-mark question. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but that only happens if they practice consistently with our weekly explainer videos. So here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Now, I want you to drop a comment below with your target grade for computer science and the biggest challenge you're facing right now. Our team responds to every single comment. Like and share this with a study partner. Before we go, I'll leave you with this provocative thought from the slide. If a negative number slips through your system when it absolutely shouldn't, it means your abnormal data testing failed to trigger the rejection logic. How resilient is your current testing matrix? Keep analyzing, keep designing, and we'll see you in the next explainer. Ace the Exams. Your Cambridge success starts here.